on oxygen. 1 mole of oxygen atom, Glenna, has a mass of, using your periodic table.
Math 15.
Right. 15.99. This, depending upon what you look at, 15.9994 is what I have up here. That's the molar mass for oxygen. Okay, so Taylor, what about chlorine? 1 mole of chlorine atoms has a mass of 35.45 grams per mole. Perfect. Now, here's the deal. If you are dealing with a compound, something that has more than one atom that are joined together in a unit, if you want to know the molar mass, and we're going to have to do that today, all you got to do is go to the periodic table and add them all up. So, for instance, we're going to pick on sodium chloride. So, for you, Autumn. So, the first thing has to do with the sodium. So, there's 1 sodium atom. I hope we're all on the same page there. 1 sodium atom because it's 1 Na, 1 Cl. So, what is the molar mass for sodium?
It is 22.99 plus.
Oh, duh. Oops, sorry.
Cl, which is 35.
Yep.
So about 65.
I love how you did that. So what Autumn did, and it's up here on the board exactly, is she looked at the decimal number for sodium. She put down 22.99 grams per mole. When you see me work these here in a minute, I'm going to just blow off the grams per mole till the end because I can.
Except I rounded.
But you're fine. You did great. And then chlorine, the decimal number is 35.45. And then when you add them together with using calculator, you get 58.44 grams. Now, that would be the molar mass for sodium chloride. All we did was add 1 sodium plus 1 chlorine. That's it. So let's do a similar thing. Pick on you back there, Billy. So what does, first off, what does LiNO3 do? Now, if you want to, you go term by term. So give me a term to represent the Li. Yep. So all we do is just write 6.9. This one has 0.941. So anyway, 6.94. That had 939.
Yeah.
See, like I said yesterday, it's like the isotopic abundances have changed over time. Well, they haven't changed. It's just a different assessment. So okay, we're back to you, Glenna. What about nitrogen? Or what are we going to add to this? 14.01. Yep. 14.01 grams per mole for just 1 nitrogen. So now I'm going to pick on you, Taylor. So now don't forget with the formula we have a 3 subscript here. So how are we going to handle the oxygen?
There's 3 oxygen. 15.99.
Yep, 15.994 I have up here times 3. Perfect. That's it. That's it. And so actually if you tap that into calculator, you're going to get the molar mass of, this is called lithium nitrate, LiNO3, of 68.95 grams per 1 mole. That's it. That's it. So the next slide, before we go on, and actually this is kind of what Taylor talked about, and we'll probably do a sub kind of little bit of what she talked about, but if you need to go between grams and, my builds aren't very good. If you need to go between grams and moles, we're going to do this on the next slide. And to do that, we're going to use the molar mass. This slide was all about calculating the molar mass of compounds. We use the grams per 1 mole to get back and forth between grams and moles of a compound. Now, we'll be talking more about this on Wednesday, I think, because we didn't do any problems. But remember what the definition of a mole is. A mole is 6.022 times 10 to the 23rd particles. So if we know moles and we want to get to particles, that particles could be atoms or molecules or formula units, we're going to use the 1 mole is equal to 6.022 times 10 to the 23rd. So that's going to be our ticket to kind of go back and forth between these 2 quantities. Moles and grams, molar mass. Moles and particles, that could be atoms or molecules or formula units, Avogadro's number. Okay, so let's do a few. I don't think we need to do all of these. these, but you got them down. I think we'll do fine with these. This actually, I'm just gonna write up the answers because I did these at my desk in order to kind of save some time. You can check them later and let me know if I didn't get them right. But when I added 3 oxygens, I multiplied 3 oxygens, used my calculator, I got the molar mass. And by the way, MM for me means molar mass. And I got molar mass for ozone is 47.997 grams per mole. And then I did for N2O, I took 2 times nitrogen plus 1 times oxygen, and I got the molar mass for that is 44.013 grams per mole. I'm trying to lay this down, see if I can get any better. And for the last one, it was the heaviest, as you might imagine, fluorines and chlorines and all that. And I got 137.36 grams per mole. Molar mass of that, 137.36 grams per mole. Now, on the next page, we're going to use these quantities. Again, I think we're probably okay with how we got those from the periodic table, hopefully. So here's what this looks like. We're going to use those molar masses to work some problems. A little bit ago, remember I had, grams in one circle and moles in another circle, and the thing over the arrow was molar mass. So here we go. So for the first one, I want to use the molar mass on the previous slide to say, well, if I have 14.5 grams of ozone, I'm going to use the molar mass to say how many moles I would have. So here's what that looks like. From the previous slide, I said just for ozone, 1 mole of O3 is equal to 47.997 grams of ozone. That was the molar mass. To work this problem, what I would do is start with the 14.5 grams over 1. Now, I am all about making units cancel. When we've talked about making units cancel before, that's what we call using the factor label method. So actually 14.5 grams, I could be more specific, 14.5 grams of O3. Okay, I'm going to use actually this equality or equivalency statement. And I want grams of ozone to cancel. So do you see with that equality, I'm going to put my 47.997 grams of O3 down here, and I'm going to put my 1 mole of O3 up there. 1 mole O3 up the top, and then the 47.997 grams of O3 in the bottom. Now I've gone ahead and you can tap it in too. When I tapped it in and rounded it to only 3 digits, I got 0.302 moles of O3. 0.302 moles of O3.
So you divide that.
You divide that, exactly. Yeah. And in this class, I'm not emphasizing the factor label method of working problems, although I think the textbook does. If you just want to memorize, divide by, that works. But this factor label method, basically taking an equivalency statement and making it into something so units will cancel, be left with units you want to be left with, will get you much further down the road in all sorts of things, including currency. All right. Now the next one, from the previous slide, we came up with the molar mass of NO2. So I'm going to put 1 mole of NO2 is equal to 44.013 grams of NO2. And in this case, notice my first term is not grams, it's moles. So I'm going to put 0.0067 moles NO3 over 1. The more you do like little problems like this, you even stop looking at the words. You just kind of focus on the numbers and the units. And so in this case, since I want moles of NO3 to cancel, notice I'll put units of moles of NO3 on the bottom. I'm trying to get to grams of NO3, units of grams of NO3 on the top. One way to do it is that way. And then all I have to do is for NO3, go back and look at my molar mass. So of course I'm going to put 1 mole NO3 on the bottom, 44.013 grams of NO3 on the top. And if you trust my math, rounding to 2 sig figs, tap it in if you want, and I got 0.29 grams of NO2. Excuse me, N2O.
I was gonna say, I was really confused. But yeah, never mind.
Oh yeah, I see. Oh my gosh.
Yeah, you were doing it the whole.
I was. Yep. Thank you. Sorry about that. Wow. I don't even know what NO3 is. Okay, thanks. Feel free to correct me, but thanks. Okay. Last one. Again, I kind of focus on the units. Notice that we're giving grams and we're supposed to come up with moles. So I won't rewrite it, but on the previous slide we had a whopping 1 mole of CCl3F is equal to 137.36 grams of the compound. So if I start with 15.10 grams of, see, make sure I get this right, CCl3F, okay, what is my next term going to be to get to, what are we trying to get to, moles? I heard a 1 mole of, yep, CCl3F over that big number, 137.36 grams of CCl3F. Perfect. Are you serious? My goodness, come back. So units of grams of CCl3F will cancel. We're left with units of moles. Yep, when we're going to divide that out, give ourselves 3 sig figs, and when I did it, around a 3 sig figs, actually 11.0 moles of CCl3F is what I got. It's got a mind of its own. Okay, so these are little problems that we call, the first one would be a grams to moles, the next one would be a moles to grams, and the last one would be a grams to moles problem. Again, kind of focusing on the left side of that figure. Last slide, the coup de grace, okay? One of the things that we've talked about, actually I think it was in Unit 1, it's funny, this chemistry class has a bunch of chemistry, but it's kind of scattered differently than I'm used to. We talked about balancing equations. And remember that we can kind of think of a brick wall, where in this case we have to have the same number of carbon and oxygen atoms on both sides of the reaction arrow. What are the coefficients? Do you remember stoichiometric coefficients? What are they in front of the carbon, oxygen, and carbon dioxide? If there's no number, it's 1. Exactly. If there's no number, it's 1. I have what? 1 carbon over here, 1 carbon over there, 2 oxygens here, 2 oxygens there. So it is definitely balanced, which is awesome. So when we balance it, we can actually kind of think of it in terms of kind of 3 different ways. I usually think of it on the small scale first. I think of 1 atom of carbon and 1 molecule of O2 will form 1 molecule of CO2. I think of it like that. I think of the kind of the relative numbers, the balancing part. Those what we call the stoichiometric coefficients, the 1 across the board. Alternatively, and I don't have a slide up here, but if we in chemistry dealt with dozens, you buy this? I could take 1 dozen carbon atoms and 1 dozen molecules, and they would form 1 dozen CO2 molecules. 1, 1, and 1. 1 dozen across the board. It's like scaling it up. Instead of just 1, it's 1 dozen. Well, instead of thinking 12, think 6.022 times 10 to the 23rd. Think moles. So I could say with those what we call coefficients with those numbers. One across the board, 1 mole of carbon atoms reacts with 1 mole of O2 molecules to form 1 mole of CO2 molecules across the board. And of course, according to Avogadro's number, Avogadro found that, or established, 1 mole is equal to 6.022 times 10 to the 23rd of anything. So the last one says, this really means I have 6.022 times 10 to the 23rd atoms of carbon will react with 6.022 times 10 to the 23rd molecules of O2 to form 6.022 times 10 to the 23rd molecules of CO2. It's just the way it rolls. I really like, the succinctness of writing chemical equations like this, and it's just like a recipe. It's just a beautiful thing. Okay?
Just coincidentally, that's how bananas always react.
That's how many what?
Always react.
Well, that, I think, yeah, that's how many relatively react. So, for instance, if we, instead of 6 times 10 to the 23rd, if we only had 3 times 10 to the 23rd, if we had a half a mole, it will react with a half a mole of O2. It's like scaling down your recipe to form a half a mole of CO2 molecules. So, yeah, it's definitely like making brownies, and you know, if you have so many eggs and you want to max out, and then you use so much flour, and you'll make so many brownies. You know, it's all just relative. So, okay, well then, that brings us to today. Let's see if I can